Hello everyone, I'm Dr. Paul Kerstetter, and in today's video we're diving into finite impulse response filters, specifically how to implement them on FPGAs. We'll explore both the direct form and the transpose form FIR filter architectures using VHDL and Verilog. I'll also show how timing issues arise with the direct form as the number of taps increases, and how the transpose form solves that problem. Finally, I'll briefly touch on Vivado's FIR compiler IP core. FIR filters for FPGAs, timing closure for direct and transpose filters using VHDL and Verilog. Let's start with a quick refresher on the theory that brings us to FIR filters. When a signal passes through a linear time invariant system, the output is the convolution of the input with the system's impulse response. This is expressed using the convolution integral for continuous time systems. Solving the convolution integral directly can be difficult, but in the frequency domain it becomes much easier. Using the Fourier transform, convolution becomes multiplication. Since FPGAs operate in the digital domain, we use the discrete time version of the convolution equation, known as the convolution sum. In the formula, k represents time steps and is equal to the sampling interval Ts. This lets us bridge the gap between continuous and discrete worlds. Let's take a simple case where n equals 2. The convolution sum equation becomes the equation shown in the slide. From the equation, we can see adders and multipliers are needed. We also need delay elements since the input xn minus 1 is a delayed version of xn. Delay elements are flip-flops. Finally, gain elements are needed for the constants or coefficients represented by h0 and h1. The convolution sum equation can also be represented graphically, which is shown below. This is known as the direct form architecture for n equals 4. One issue with the direct form is that it chains multiple adders and multipliers between input and output. As the number of taps increases, so do the logic delays, which can lead to timing violations on the FPGA. To solve this, we use the transpose form FIR filter. In this architecture, the same equation is implemented differently. Instead of chaining many adders, the structure distributes them more evenly between flip-flops, reducing the critical path and improving timing. Okay, that's the end of the refresher. In the next part of the video, I will demonstrate the VHDL and Verilog implementation of the direct form and transpose form FIR filters. The outline of the demonstration is shown in the slide. First, I will discuss the direct form FIR filter and show the timing results difference between the 3-tap filter and a 21-tap filter. I will show the worst-case timing path. Next, I will discuss the transpose form FIR filter and show how the 21-tap version doesn't have timing issues. Finally, I will briefly discuss Vivado's IP FIR compiler core. First, we're going to start our project. And just a note about the code. In this project, I have the direct form and transpose form filters both in VHDL and Verilog. And that's available in the link in the description on GitHub in case you want to get those codes files. But one of the most important things about the code is it's an adjustable length FIR filter, and you can change the length here. Right now it's set up to be a 3-stage filter. When you set it to 2, that means it's a 3-stage filter. It has an input to the filter and an output to the filter. And this is a boxcar filter that's being implemented. And in this case, that means all the coefficients are 1. So in this case, since it's a 3-stage filter, it should have 3 1s for coefficients. And that boxcar filter, by the way, is a simple averaging filter. So there's the code, and the code can be found in the project. Also, I have constraints in this project, and the constraints are for a ZCU 104 board, which is a Zinc UltraScale Plus device. In the constraints, there's input and output constraints, there's clock constraints, and there's input delay and output delay constraints. And that too is available in the link in the description on GitHub. And then finally, there is a simulation test bench. Those are available too in VHDL and Verilog in the link in the description to GitHub. So the first thing I'm going to do is we're going to look at the length of this filter by looking at the code. Here we have the length set to 2, which is a 3-stage filter. And then we're going to run the simulation on that. Okay, we're going to expand the window. First, we're going to look at our input pulse. And as you can see, there's our input pulse, unit pulse. And if we expand on that, we can see the unit input pulse is actually 2 clock cycles. And our output pulse is 1. It's a 1 on that rising edge of the clock. It's a 1 on the second rising edge of the clock. And it's a 1 on the third rising edge of the clock. And it's a 0. So that's 3 coefficients of 1. That's what we expected. I'm going to minimize this simulation window. The next thing I want to show you is the schematic for this. What does the schematic look like? To find that out, you go into RTL analysis, open elaborated design, click on schematic. Okay, we're going to expand the schematic. So the schematic has the reset flip-flops here, and it has the 3 delay element flip-flops here. They're stacked on top of each other because it's an 8-bit bus. And the longest path is from here, the first flip-flop in the filter, and the path goes up here to a multiplier, to an adder, and then to another adder. And imagine what if there was a flip-flop on your output here. You would have to meet timing. And so as the stages grow in this flip-flop, in this FIR filter, the more adders you will have that will be in between the first stage of the FIR filter and the output flip-flop. And so that could cause timing issues. So there we go. Now we're going to do is we're going to go ahead and implement this design and see if it passes timing. To do that, I click on the Run Implementation hyperlink. Okay, so our implementation run is done. Now what I'd like to do is examine the timing. And you can get a report on the timing here. And it says our worst negative slack is 2.752 nanoseconds. Our worst hold slack is 0.040 nanoseconds. First pulse width slack is 4.725 nanoseconds. So our timing passes. But what would happen if we expanded the number of stages of our filter to 21? So to do that, I have to go to the boxcar filter VHDL code, and I have to change the length integer to 20, and that will give us 21 stages. And now I will go ahead and run the implementation again. We'll open the implementation design. We got a critical warning message, and the critical warning message is the design failed to meet timing requirements. So that's what happens when you do 21 stages of a direct form FIR filter. Oh, and by the way, the clock frequency is 100 megahertz. As you can see in our timing report, click on Report Timing Summary, which is right there. And you can see the worst negative slack is minus 2.932 nanoseconds. And we have total negative slack of minus 40.735 nanoseconds, which means that we're failing in more than one path. And if you want to see what path that we're failing it in, or what paths we're failing the timing in, you can go up here to, so you go to Reports, and then you go to Timing, and then you can go to Report Timing, and that shows you the paths. Let's open the implementation schematic. The worst path is shown on top here, which is minus 2.932 nanoseconds negative slack. And if we click on that, it shows you, let me expand the schematic window so you can see, but it shows you the path that it has to go through in order to get to the output. And so as you can see, there's so many delays that have been introduced into this path due to the adders that we've failed timing with this direct form FIR filter. So let's switch over to the transpose form filter. And I have that project already made. Okay, let's open up the transpose form filter, VHDL code, and we will switch the length to 2, save. And let's take a quick look at the schematic. Okay, let's expand the window, and you can already see the difference for this 3-stage FIR filter transpose form architecture. And you can see that the pluses are in between the flip-flops. There's a plus in between the flip-flop. There's a plus in between the flip-flop. And so this has a better chance of meeting timing. So that's what a 3-stage filter looks like. Let's go back to the code and see if the 21 stage passes timing. So I'm going to put the length to 20. That makes it 21 stages. Let's run the implementation. Click OK to open implemented design. Click on Report Timing Summary. There it is already. Okay, for the 3-stage, actually for the 21-stage filter, we've passed timing. We didn't get a warning this time. And let's just take a look at the reports. Let's open up the schematic in the implementation view. And that's what our FIR filter looks like in the transposed architecture. Let's click on path 21 since that's our worst negative slack. And let's look at the schematic again. And that's the worst path right there. It doesn't have many elements in the path, but it does have quite a long trace length. So finally, the last thing I want to show you is how to find the FIR compiler, which comes with Vivado. To get that, you click on IP catalog. You click in FIR, expand this window. Expand this window a little bit here. FIR compiler, there it is. So double click on that. And this is a IP core with an AXI bus on it. And it does FIR filters. And you can put your coefficients in there. So this is all set up to make your FIR filters for you. So the question is why would you want to hand code your FIR filters rather than use this GUI, which is automatic? And one reason I found was that the GUI uses DSP slices, and it didn't look like there was a way to turn off the use of DSP slices. So I had a case at work where I I was using up all the DSP slices in my Zynq UltraScale Plus FPGA, and there was no way to turn them off in that GUI compiler. So that might be a case where you might want to hand code your own FIR filters, so that or don't use up all your resources. Well, that's all for now. If you found this helpful, don't forget to like, subscribe, and hit the notification bell for more content on digital signal processing and FPGA design. Drop any questions or topics you'd like to see in the comments. I'd love to hear from you. Thanks for watching, stay safe, and I'll see you in the next video.